Okay, so lecture 2. Okay, so we are dealing with the second order system. So it's good to study second order systems before you move on to much larger systems. Okay, and specifically useful for visualization purposes, because when you do you can see 2D things, you can plot them and they make sense. If I tell you a 10th order system and you want to visualize it, all the states at once, that will be difficult. So second order systems, actually visualization is better, right? And the things that we can do easy, like something like a phase plot. You can go up to 3D and you will see, you can try 3D phase plots and they will get complicated. So, but 2D phase plots will be good. And basically phase plots are nothing but you start at different initial conditions and see how all trajectories are kind of going. So basically trajectory plots plot. Okay, so we will, our second order system will be consider x dot equals to f of x, for example. Right now, just let's consider time invariant autonomous systems, means no input, time invariant, something like this, where x equals to x1 and x2, just two states, simple as that. So that means your f of x will be equal to f1x to f2x, right? So, and if we draw some trajectories, like just your phase plots might look like this. I'm just giving an example. For example, inverted pendulum without friction will have trajectories like this. You can see, it makes sense. I don't know if let me make it. So it doesn't matter wherever you start, you will start just oscillating wherever. So I'll connect all the dots later on, but this picture, like if it is x1 and x2, which is inverted pendulum with theta 1 and theta and theta dot, two states, right? So you will see that it's just whatever initial condition you choose. Let's say I start here, you will keep rotating on that, so without friction. So these will be the trajectories of a inverted pendulum, not on card, just simple inverted. This guy, right? So this is theta. So if there is no friction, wherever you leave, this guy will keep just rotating, right? Make sense? Like there is no energy is not dissipating, and it just keep going circles. So that's how the trajectories will look like. Okay, so that's. So next thing is like qualitative behavior is important. Even second order systems, like what are we doing? We are solving the ODE, right? So we have this x dot equals to f of xu, right? And or x dot equals to let's say x1 dot equals to f1 of xu, and x2 dot equals to f2 of xu. This is not linear, right? This is not a linear system. So even solving this, I remember you guys when you were doing time varying systems and you have to find that state transition matrix, it was a pain in the butt, right? Like so just think that was a linear system. Even it was time varying, but it was a linear system. Now you're solving for nonlinear systems, even if they are second order. Getting an exact solution is not not possible, or not. So that's why you need the phase plot, approximate plots that can help you visualize how the system is converging or behaving, right? So qualitative behavior. So what is the best thing is like linearization is used here. It's qualitative behavior. So we can have a x dot equals to ax, and if you remember, if we start at any initial condition, the solution, what was the solution for this equation? Do you guys remember? If x of t equals to e to the power a t x of 0, right? So that was so simple, like it's a closed form solution for the second order system. So this also we can use. So what we can do is we have a second order nonlinear system. We can linearize it around the equilibrium point, right? So we have equilibrium point somewhere, let's say origin. You can linearize it around it, and you can still put that system into this form, right? And then you can use all those eigenvalues, eigenvectors to visualize what happens at least near the equilibrium point. Okay, so or using if you remember eigenvalues decomposition or diagonalization, if you remember our technique, you can write A to be A mu inverse J. Notation is different. This is the transformation matrix, if you remember. You remember a similarity transformation to do the diagonalization? If I have this J matrix is the Jordan form. Jordan form, if all the eigenvalues are real, distinct, they will appear in the block matrix, right? So so that and why we used to use Jordan form? Because e to the power at for a diagonal matrix is very simple, right? The A is become all the lambdas. So it was very if for example if A is lambda 1 zeros 0 lambda 2, that's a diagonal matrix, right? What is e to the power at for this? It is e to the power lambda 1 t 0 0 e to the power lambda 2 t. So it was that easy to compute e to the power at if A is a diagonal matrix. So it's always beneficial to first convert A into a Jordan form and then find. So then you can write, x dot equals to mu e to the power j t mu inverse x0. Same thing, right? This is nothing but A. And okay, so that from previous only. Okay, or you can say, like, if you can also say that you have a new state Z for the new matrix. If we are directly dealing with just J, that means J Z equals to mu inverse X is one state transformation. This is like Z equals to XT, similarity, or TX, similarity transformation. You convert. So instead of using X, when we use Z, the matrix is diagonal, right? So that solution is easy to visualize. So instead of saying X of T, you have now Z of T. These things will not be there, right? In that case. So your Z dot is now e to the power Z dot is basically JZ, right? So ZT will be what? E to the power JT into Z0. And this is a diagonal matrix. So the solutions are easier. But Z is not the actual state. It's the transformed state. Okay? But getting back it is easy. So first you solve for Z, and then if you want to see the real picture of X, you can do a similarity transformation, because there is a relationship now, right? So X will be what? X will be mu Z, basically. Okay, again, just for the understanding of it. So now it's so if you solve so for example x dot equals to ax, right? This is a second order system. You can find eigenvalues, right? How do you, so lambda, you can get a characteristic equation like lambda I minus a, right, equals to 0. You can solve this and find the eigenvalues. How many eigenvalues will be there? 2. So that's life is easy here. We're not going for more eigenvalues. So how many cases can be there if you see? There can be an eigenvalue like this, right? One case when they are both distinct, right? Real and distinct. I'm not talking about negative, positive right now. Just eigenvalues are real and distinct. You can have eigenvalues repeated, lambda, lambda, 0, k. Now k can be like 1 if you remember in Jordan form there, right? Or you can have, third is when eigenvalues can be complex also. They can have an imaginary part as well. So that system becomes alpha minus beta, beta minus beta alpha. So eigenvalues of this form, right? Alpha plus minus j beta. So alpha is the real part and beta is the imaginary part. That we didn't deal with in the last class, right? So if you have complex eigenvalues, your Jordan form will look like this. We can verify that. Okay. So you have these 3 kind of possibilities are there in the Jordan form. And why we are talking about it? Because we want to see the geometry near the origin. Okay, depending on what signs it have, you can have a geometry near. So I can give you one example here. So one example will be, so case 1, for example. Case 1 will be, you have eigenvalues real and non-repeated. So means real and distinct. Means this case, right? Lambda 1, 0, 0, lambda 2. So let's talk about the solution. So this is for J, Jordan form. A is not that way. Means we are saying that the Jordan form of A is this, right? This is not A matrix, it's the diagonal matrix. So we are always talking in the transformed solution. So my Z equals to, so your X dot equals to AX, right? And Z dot equals to JZ, where Z equals to mu inverse X. Right? So remember this is J, not A. So we are first dealing with diagonalized. We want to see how the diagonalized solution look like. Basically it's a rotation matrix. You rotate it in the direction of Z1 and Z2 basically, right? So the solution looks like this, right? ZT will be e to the power lambda 1 t 0 0 e to the power lambda 2 t, right? Into Z1 0 Z2 0. So the solution will be what? Z1 t equals to e to the power lambda 1 t. So they are not mutually dependent. See, one state does not depend on the other state, in this case at least, right? Z1 0 and Z2 t is e to the power lambda 2 t Z2 0. So that's the solution. Right? So how do you think this should look like? And if I draw a plot for this, I want to draw. So you have Z1, this axis, Z2, this axis, right? So exponentially, wherever, for example, I start here. So both Z1 and Z2 go to 0, right? So basically like something like this. Anyway, it doesn't matter where I start. Trajectories look, if I start here, right? Doesn't matter where you do this kind of plots will, some parabolic curves will be there. This okay. So depending on whether lambda 1 is greater than equal to lambda 2, so if both are positive, what happens? So if both are positive, what happens? So if both are positive, let's say, so this is Z2, this is Z1, what happens if both are positive? Doesn't matter where you start, you're basically moving outside, right? Your direction is basically outwards because you're exponentially growing, right? Similarly, anyway, it doesn't matter where you start, you're basically moving outside.
Isn't the curvature concave? Like, isn't it exponential? They have this shape, isn't it?
No, this is not. Exponential curves are always like this, right? If you don't remember, like exponential. So if I start here, this exponential curves are. Yeah, it's not. They are not straight lines.
But it should, he's saying it should go up.
Yeah, so they are going up, right? From if I start here, or it doesn't matter where you start, it's moving in this direction, right?
But that's saturating at a value.
The slope,
The
should
slope here
increase.
should be right.
Oh, yeah, it's slow basically, at the end, infinity it will go. Yeah, the slope something like keeps growing.
It should go, like the slope should grow exponentially as well, right?
Yeah.
Okay.
But you have your slope decreasing.
Yeah, I might have drawn wrong picture here. Maybe show you, let's see if I have a proper picture. But yeah, you're correct. It's exponentially. So this like keep growing. I'm just talking about like this picture till here. So you're saying this should not decrease, right?
No, it should look more like this should decrease and increase like that. No?
So you're saying first it should increase?
First, the
It should
slope
decre-
should be less, and then the slope should increase.
Mhm.
Right here, you have a high slope that decreases. That looks more like a square root almost curve.
Well, let me get to this. I don't think that's correct. Let me check. Because there is a ratio here. Like we are talking about. You're not just what you're thinking is this. Just only one variable, but we are talking about this is the ratio of z1 and z2. So for example, I say what is z1t by z2t equals to e to the power lambda 1t or e to the power lambda 2t z1 0 by z2 0, right? So it's a ratio. So depending on lambda 1 or lambda 2 is greater than this will be kind of it is, yeah. So if you're correct, if it was a timeline, the plot that you are thinking is time versus
Whatever.
z1.
Yeah.
But now it is not that. It
It's
is
a
not time
ratio.
versus. It's
Okay.
it is z1 versus z2. So yeah, for 1 second you got me, but it is not time versus that plot. It's the ratio now we are dealing with, right? Because you're plotting both. So depending on which one is greater, it depends on that. Similarly, if lambda 1 less than lambda 2 is less than 0, then these things will be incoming towards the origin. Okay? So what we do is we categorize this into, so this kind of plots like going out. Again, this is not correct, but so these are called nodes. If eigenvalues, this kind of picture, so you will see that near equilibrium, this will be the picture, right? If you have an equilibrium and in z1 z2 plane, right? So this is z1 z2, this is z1. So this is called unstable node. So we categorize them, right? Now we are talking about pictures. If your eigenvalue comes out to be real and distinct but positive, this is called categorized at unstable node. Okay, so the picture, the phase plot on a bigger picture, near origin, your curves will be coming like this at least. Okay, wherever you start at the end. And similarly, if eigenvalues are negative, it is called unstable or a stable node. Okay, so stable and unstable node. eigenvalues real. So we can see a table later on. Like I can see if I can bring that picture here. Okay, can you add pictures to this?
So by stable node, you mean for like a area of initial conditions, it's stable or unstable?
Yep.
Okay.
So we are talking if the equilibrium point and the eigenvalues comes out to be positive, then it is a unstable node. And if they come out to be negative, then it's a stable node. Unstable and stable, right? So whether curves are coming to the origin or whether curves are going away from the origin, that's the thing. Whether it's attractive or repulsive. Attractive means stable, repulsive means unstable. Okay? So that's the case here, right? So right now, so that's one case. Another case, interesting case is this. When in same case, so we are still dealing. So you have, so one is lambda 1, lambda 2 is greater than 0, right? That's one case, man. That's unstable node. And second is lambda 1, lambda 2 is less than 0. That is a stable node, right? There can be another interesting case where one eigenvalue is negative, one is positive. That also is possible, right? So what happens there? So in one curve, if you see, so for example, in this case where lambda 1 is less than 0 and lambda 2 is greater than 0, what happens to that picture? So you have, see, your z1t, for example, is e to the power lambda 1t, z1 0. So one curve is going to 0 for sure, right? So z1 goes to 0 no matter where you start. And z2 t e to the power lambda 2t. Now because lambda 2 is positive, z2 has to go to infinity eventually, right? So how does this plot look like in terms of z1, z2 and z1? This will look like, let's say I start here, right? So it looks like this, z1. So this is z2, sorry, z2 is, oh, I'm sorry here, I'm doing the wrong thing. So let's say, I'm doing this case when lambda 1 is greater than 0 and lambda 2 is less than 0, right? So this is positive and this is negative. So means z1, so it doesn't matter where you start, z2 has to come to 0, right? This direction. So z2's direction will always be this, because z2 is, lambda 2 is negative, and z1 will always go. So these pictures will look like this, right? So right. So this is called saddle node. So if you have seen horse's saddle, so one side it increases and one side it decreases. So it's called saddle node. Interesting picture. So you come and then you leave the origin. You come towards the origin and you leave it in one direction. So you're always coming from this direction or this direction, but you're leaving also then, right? So we'll see how at the bigger picture, when we use some phase plot tools for a real nonlinear problem, you will see this similar behavior near the origin. But now, just by eigenvalues, you can tell what will be the behavior of trajectories near the equilibrium point, right? So that's called saddle node.
So this is what you meant yesterday when you told eigenvalues determine the shape, how...
Yeah, this is exactly what I mean. Means eigenvalues determine the nature of curves near the origin. Okay?
When you say near origin, you mean?
Near the equilibrium point, yeah. Origin is always like, you can always okay? Got it? So let me now just okay. So now what are we doing? So this was what these pictures were for actual x dot equals to ax, right? But now we are talking about nonlinear system, f of x, right? So you can always linearize this. So that is delta x dot equals to a delta x, right? So basically what I'm saying is you will exhibit the same behavior near. If it is a linear system, that doesn't matter where you are. It will exactly follow the same thing. But we are talking about this now, right? We are talking about deviation from the equilibrium point. Delta x is the deviation from the equilibrium point. So we are saying that this can still give you a picture if you linearize it, the system, near equilibrium point. So delta x is x minus x equilibrium, right? So we are dealing with the deviation now, and this A matrix, this eigenvalues gives you that whether when I perturb it, what will happen to the system. And if you have small enough perturbation, then this kind of behavior will be there. Okay, so that's the thing we have here. Okay. And if you see the book, there are other things also, like what if there are some place where eigenvalues are 0 also, then they are straight lines, right? For example, if lambda 1, lambda 2 equals to, so if basically if lambda 1 equals to 0 and let's say lambda 2 is less than 0, so you have z1 equals to z2 0, right? Because this is 0, e to the power lambda is 0, and then you have z2 is z1 0 and z2 0, e to the power lambda 2 t. So what kind of plots they will look like? They will look like
G2 is decreasing.
z2 is decreasing,
Z1 is constant.
not equal. Yeah, no. I'm just thinking. I think they will look like some. I was thinking what they should look like. Some kind of straight lines, right? Something like this. So lambda 1 stays the same, right? So whatever z1 you start with stays that, right? This is z1, this is z2. So z2 goes to 0 for sure. So these kind of plots will be there, right? Because z2 goes to 0, z1 stays the same. So right? So you can see, and you can transform when you rotate it, they might look like something like this along v1 and v2. So again, it gives you a picture. So again, it's a math of these two eigenvalues, e to the power lambda 2t. You find the ratios and you see how the curves look like. Okay, so just the gist of it. So I don't have to go about linearization, right? So linearization you guys already know, but let's take an example. So our simple inverted pendulum, right? You remember our inverted pendulum, this one. Theta, I think there was an equation. What was that equation? That was, so our x is equal to theta and theta dot, right? And theta double dot was minus g by L sine of theta minus k by ml theta dot. Okay, if k is the friction, so we can write, right, x1 dot equals to x2, right, and x2 dot equals to minus g by L, what is that, sine of x1 minus k by ml of x2.
I think it's only m there. K by m.
K by M where?
Instead of ML.
No, it should be ML, I think, because it is ML squared. Is it just K by M?
I think.
Yeah, K by M, sorry. So K by M, yes. So if you make them equal to 0,
I was like, how do you know that?
if it is equal to 0, so our equilibrium point is nothing but n pi by 0, right? So this is x1, this is x2, equilibrium point. So there are basically two equilibrium points. So now you want to linearize it and see what happens as these two equilibrium points. So let's say when I linearize this equation here, del f by del x equals to, with respect to x1, 0, with respect to x2, 1, and with respect to x1 it will be minus g by l, what's that, cos of x1, right? So we are doing with respect to x1, good. Then with respect to x2 it should be minus k by m computed at n pi and 0. So let's first compute at 0, 0. So when I put 0, 0 means my equilibrium point I choose to be 0, 0, or, right?
Yeah.
So that will be 0, 1. What is, if I choose 0, cos is 1, so minus g by l minus k by m. Okay. And let's assume that g by l somehow, my length is equal to 1. So L equals to 9.8 for convenience, and K by L is also equal to 1. So what does that give me? It gives me 0, 1, minus 1, minus 1. A equals to this. What are the eigenvalue? I'm trying to see if it's a stable node or something more. So if we find the eigenvalues, it will be lambda minus 1. What is that? 1, lambda plus 1, right? So it will be lambda square plus lambda plus 1 equals to 0. Right? Now we can compute what's that? What are the roots for this? It should be minus 0.5 plus minus j 0.866. I'm just writing down. You can compute. You remember that? If you have a square plus b square, so it will be minus, so it's like, this is, what is that, plus minus b plus minus square root of, what is that, a square minus 4ac, sorry, b square minus 4ac, right? So these are like coefficients. If there is a coefficient a, there is a b and c, right? So a is 1, b is 1, and c is also 1. So you can plug those things here and you will see it is divided by 2 also, right? 2a, right? So divided, so b is 1, so it's 0.5 for sure, minus 0.5, and then it is 1 minus 4, so that is what, minus 3, square root of minus 3, right? So that is like, so that will be minus 0.5 plus minus j root 3 by 2, and root 3 by 2 is 0.866. Okay, so that's how. So now what category it is? Tell me. Is this, in terms of pictures, what is this? Is a stable node, unstable node, stable, what is that, focus, unstable focus, what is that?
Into a stable spiral, isn't it?
Yeah, it's a stable focus, right? So it means the picture will look something like this, right? So
the arrow's going into the
yeah, and similarly, if the eigenvalues are, so what will happen if I choose pi instead of 0?
Probably an outward spiral.
This will become, so now this becomes 1, right?
Wait, would it be outward? It would be unstable. But
And now it becomes minus. So now it becomes -1 here, right, somewhere. So instead of so 4AC, because C is positive, it becomes one eigenvalue will come to be unique. All the eigenvalues are positive actually. Am I right?
It will be plus.
So lambda square plus, so it is lambda square, wait, let me do it again. It was, so it is lambda -1, right? So 0 is lambda -1, this becomes -1, lambda +1, so it becomes lambda square plus lambda minus -1, right? 0, so you can find roots for this. And they come out to be, no, actually 1 comes out to be negative 1.618 and 1 comes out to be 0.618. So what do you think it is? It's a saddle node, so it comes from one side and then leaves. Okay? Got it? So let me, like, we can try face plot sometime, but let me see if there's a picture somewhere. So x dot, so see, we are dealing with this equation here, right? In linear system, this was x dot equals to ax, and existence, uniqueness was not a problem. Okay. Now, when we are dealing with nonlinear systems, we have to first deal with the question whether is there a solution to this ODE, even if we don't know. Finding exact solution is out of bounds, like we don't know how to find exact solution. Yeah. But can we even just look at, can we do some mathematical operation treatment to this and say that if these conditions are satisfied, there is an solution and that is a unique solution? Because if f(x) does not satisfy those two kinds, then you're basically wasting your time. Because let's assume a system where solution is not unique or does not exist, then is that a system? We should not use that system, right? Like, I want a controller where you can guarantee that I will reach there or I hit the missile. So you need a unique and solution which exists. So we have to come up with some mathematical conditions on this f(x), which will determine if that conditions are satisfied. We can always say that there is a solution which exists, or at least nothing, even if a local solution, that I can guarantee that solution exists within this boundary, and go ahead with and deal with it. So maybe couple of lectures, maybe just 2 lectures, we will have to deal with this mathematical. Later on, we will always assume that there is a solution which exists and it's unique. It is always in the background that function will always satisfy that condition, right? So bear with me for next 1 or 2 lectures dealing with this. It's important. You guys are graduate students. You need to know when you write a paper or when you come up with a function, without wasting time, you should say, oh, I don't know if there is a solution that exists or not, right? So I think in couple of 1 or 2 lectures, we will deal with mathematical preliminaries, like some definitions. Stability and all you guys already know, but some norms, and then dealing with Lipschitz conditions, which kind of guarantees that there is a solution. Right now, we are not even talking about a stable, unstable thing. Just, is there a solution? Unique solution to the system. And it turns out like stable systems always have a unique solution. We will connect that to them. So you see the curves that were coming, right? Like this to the origin. So that means there is a solution which exists and also unique, depending on where the initial conditions are. Yes, question.
So will we be meeting here Friday? Or is there a need for a help session? Because there's no class Monday, right? Monday's a holiday.
Let's meet on Friday, I would say.
Okay.
At least catch up as much as we can push
Okay.
things. Let's push, and then so that we come to that interesting part as soon as possible. The
Okay.
controllers and derivations and all that. So. But how are you feeling? Like overwhelming? No. For now, it's okay, right?
Yeah.
So I might post some assignments today for just for this part. Some this
Okay.
draw, and I will also put a face plot MATLAB file where you can put in these two
Oh, okay.
functions and play with face plots. Okay. I think it comes as a part of assignment to draw some face plots. So yeah, that reminds me I need to give books to you guys.
Yeah. I just realized one of your pages is ripped out
Yeah.
on chapter 2.
Only chapter 2 is
Huh?
only whole thing or just one page?
Just one page in
Okay.
chapter 2. Like I was flipping through while you were.
Yeah, that 2-year-old kid, 3-year-old kid.
That's what happened. He was trying to read it, huh?
Yeah.
Yeah. Here you are.
Yeah, I know. I don't think you have missed a lot there. But okay, questions? No questions? Nothing? Feeling comfortable so far?
So far.
Okay. Yeah, it will be, as I said, it's a very fun, like, it makes sense, you can connect. It's a fun class, yeah. Everything is new.
Yeah.
Like, you do any problem and you might be the first one doing it or something like that. Sometimes. So that's
Okay.
the part. I'll see you on Friday.